And the advanced circuit analysis is also the content we should learn in this semester. But the situation is we have some special cases, right? So everybody, you guys is not here, and we cannot see the online video as well. So if we can learn anything in that semester, actually, so it's better for us to start again. So the motivation, okay, so I don't want to talk about the motivation here because it's really, it's right. The circuit is very good model for theoretical analysis, is the first reason. And the second reason is this one is the most basic course for engineers. If you know, if you're trying to understand our courses, you should know this course first, right? You already learned the electric machine, right? So you find it's really hard to learn that course without this concept. Okay. Now, this first chapter is the basic concept. In this chapter, we should learn the SI units. Do you know SI units? Yeah. And the charge and the current. Do you know what is it? So, it is the source of the electricity, right? So, without this charge field or current, we don't need to analysis this, right? Okay. Right. So this one is basic variables. And for sources we have current source and voltage source, right? So do you know what is the generator in PG?
Generator in PG.
So, introduction of the electric power system. Do you know how do we get electric? Do you know how do we get electric? So you can see we use the electric here, right? How do we get it?
Who can use the generator?
You can see here we have some building inside this figure, right? The generator, the transmission, and
Distribution.
distribution and devices, automation devices, and in the end we have residential consumers. Or we can have industry business consumers, right? So this one is the electric transformation system, right? So in the power station, or we can say in the plant, we have the coal or other type of energy, and we transform it to the electricity, and then the electricity will follow this transmission line to our residential consumers. Okay, the two main objectives of these electrical power systems. The first one is to distribute and convert energy between various forms. Do you know what type of energy do we have?
Here?
Yes,
The single phase?
energy, the type of energy, do you know? We have coal, right? Okay.
Coal energy?
And we have gas, right?
Yes. Solar.
Yes. And other things?
Hydro power plant.
Yes.
Water.
And water?
Water.
And
Gas turbine.
Yes.
Wind turbine. Wind turbine.
Another?
Wind turbine.
Yes. And another? Nuclear, right?
Nuclear.
Okay, but can we use the energy directly? Because the energy we use directly is electric, right? And for other type of energy, we cannot use it directly. Instead, we need to transform it to electricity, right? Okay, that is the one main objective of our power system, and another one is to transform, right? So we need to gather, to store, and to process, and to transform energy or information via our power systems. Sorry. Wait. Would you put my up?我12点多10点。这样你现在这个上课不用跟你讲吗？Okay, so what is the circuit? So the first thing we need to see the definition of a circuit. An electric circuit is an interconnection of electric elements. So the element is the basic thing of the circuit. So this one is a single connection of electric elements. So the battery is like source. So then it's like load. So this one is the circuit mode from the real circuit. Okay. But the circuit mode is a figure, right? So use your mind to think about the model. What is the circuit model? This one is the circuit model figure, right? So what is the circuit model actually?
This is the diagram. You
Yes,
see
this
that
one
is
is diagram. This one just diagram. But the model we see generally is not a diagram. It's an equation, right? So our job of this course is to find out the model or the mathematical model from the real circuit or the circuit model figure. Okay. This one is the circuit of a radio transmitter. So we can see many electric circuit inside. And here we have resistor, like the red spot, and capacitor, like the blue one, and inductor, like the magenta, and the transistor, like the red. Okay. So the transistor, do you learn it? Yes. Do you learn it in other course?
This analog circuit.
Yes. So everything about the transistor we will learn in the analog circuit. So we didn't talk about this one in our course.
EMOS effect, transistor effect.
Yeah. Okay. So for our circuit analysis, we focus on circuit area, and we should know how does it respond to a given input. That means, do you know input? The input might be a signal, okay?
Yes.
A signal. What is the signal in our course?
So voltage signal or current signal.
Yes, U and I, right? U and I is the input signal of our circuit. If we give an input in one point of the circuit, so we want to know the response of other circuit elements, right? We want to know the voltage of it, we want to know the current of it. So that is the purpose of our circuit analysis. We know we have a circuit diagram, right? So for our course, most of the cases is a circuit diagram. And when we get the circuit diagram and we want, what do we want if we get a circuit diagram? In the circuit diagram, we have this force, and this force is the general input of the circuit. Okay, so we want to know if a circuit has a source as input, so we want to know the response of other circuit elements. Okay, the units. So all of us say you know the International System of Units.
Yes.
In your primary school?
Freedom.
Okay, right. So this one is a simple table, and you can see there were many SI units inside here, but
It's smaller and bigger.
yeah, but the bigger one is the capital, right? And the small one is the
is this opposite? This
Yes,
same, but
it's
opposite.
But I want to tell you guys is this 7 SI, maybe SI units is the most frequently used SI units. Okay, so we need to remember this one C, M, mu, N, and the big one, the K, the M, and the G. Okay.
I did not.
So here I say the reason to use the SI units because here you can see here this one is a very long day, right?
Yeah.
So when we do the calculation, it might be difficult to write it down, and it is maybe if we don't use computer, we might be easy to make mistake, right?
Yes.
So it is better to change the unit and add the prefix.
You can say your signature.
Okay. So here the basic SI unit. So now we're going to 1.3, the charge and current. In this content we should know in front of you, right? Yeah. The charge key is the electric property of the atomic part of which measures in atoms. So we know the charge and we know the unit, this color. Okay, here is a diagram of carbon atom structure, and you can see inside here, outside here we have a minus, right? Here, the minus is electrons. And inside here in the middle we have protons and neutrons. And we should notice the electrons has negative charges.
And proton is positive and neutron has no charge.
Yes, and the protons have positive charges. And we should know the unit charge is E equal to 1.6 times 10 to the power of minus 19 coulomb. And we can see the unit. It's very small, right?
Yeah.
Very small. So this one is a simple charge. So in our life, maybe the things we have many electrons inside. Okay, so the electron is the most basic one. So everything should be the times of it.
And this one is
The basic one.
yeah, and this one is less weight in the world, in our universe, because this weight is 9.11, 10
Yeah.
inverse 31 kg. So
Yes.
less.
Okay. So now we're going to see the effect of electric charges. There is one figure, right? So on the left you can see there is a comb, and the small boy with this comb brush the hair, and okay, my hair is quite long, but your hair, you have short hair. So when you brush your hair, you might see your hair is attracted by the comb, right? Okay, so here this one is another figure that is in winter. When you remove the sweaters and
Like this roughly.
yeah, when you remove your sweaters,
Roughly you see.
yeah, yeah. When you remove the sweaters,
Still
and,
this one is coming.
yeah, when you remove the sweaters, what will happen?
This making a sound.
Yes, back.
And last year, when I am going to bed in this winter, this cold, I just opened my fridge. I saw some spark.
Yeah,
This little spark.
yeah. That is the effect of electric charge in our life. Right. So there were important points of charge. The first one you should know is the charge unit, this column. And the second one, we should know the single electrons is this one. And the third one, the charge is always multiple of electron charge. We don't have one point E, right? So the fourth one, the charge cannot be created or destroyed. existing in the natural. Okay. It only can be transferred from one item to another. Right? Do you learn the electrical magnetic field? Do you learn electric magnetic field?
Magnetic
Yes, magnetic field. Do you know it?
Yes.
Did you learn it in primary school?
Yes.
Okay, so in our course or in our major, right, we focus on two things. The first one we say is the electric field. The second one is the magnetic field, right? So in our line between around us we have electric field and magnetic field at the same time. Okay, but who produced them? Who produced those two fields?
Who?
Yeah.
Current.
Current produce what?
This electric and magnetic both together. You said
It sounds
like
right.
like this way, if this electric field, this magnetic field,
Yes.
we find the electromagnetic wave.
Yes,
This way.
yes.
This total is 90 degree, 90 degree.
Yes, but generally we say the charge produces the electric
It
field
is and magnetic.
and the current produces the magnetic field. Okay, so the next important thing is the current. The current, the definition is here, it's a movement of charge. So the unit is ampere. It is also, say, coulomb per second. So generally we use ampere. The mathematical relationship of charge Q, current I, and time T is here. So this one here, the differential form, and here the integral form. But in our course, do we use those two equations?
I see also circuit.
Do we use those two
Yes.
equations in our course?
I use for some of the
Use
example.
maybe some cases, in most of the cases, we didn't use it to get our current, right? So generally we write maybe KCL or KVL to get our V or to get our I, right? So this one is just a definition of current. We seldom to use it to get our current in the real world. What is the reason? What is the reason? The reason is, okay, just look at this equation. We can see here in the denominator or numerator.
Denominator.
Okay, in the denominator, right?
Yeah. And
We have dq.
Yeah.
So how do we know a dq in the real world? How do we know a dq? We know q, right? How do we know it? We don't know, we cannot measure it, right? Or we say, generally we just get the voltage or the current. We didn't get the Q. Okay, so that is the reason why we seldom use this equation. It's just for definition. We should know the I. Okay, we should know, well, we should know this equation, but we seldom use this equation. Okay, now we're going to have a look at the direction of current. From the definition, we know
this is the electron direction and this is current direction.
it's like this. Do you know?
Yes.
So the direction of
Of
a
current.
current is
Positive.
positive electrons move from the positive sign. Okay.
High potential to low
The
potential.
direction of the positive electron moves, right? That is the direction
Of current.
a current. So, but actually it's not right. So the actual direction is like this.
Yeah, this is the electron direction.
Yes,
This
this is the
electron.
real direction. But in the beginning we don't know. In the beginning we don't know this. So we say the direction of the
Correct.
quantity is right.
Yeah.
But why we didn't correct it?
Can you again?
Why we didn't correct this mistake? We know this is a mistake because we say we define the direction of positive electron as the direction of a current. But the real direction of current is the direction of
Of negative.
negative electrons. Now we know it's a mistake. Why we are not trying to correct this mistake? Why? Why we didn't correct it?
For this battery, this electron is moved from low potential to high potential, and current is moved from high potential to low potential. Current and electron is moved this opposite direction.
Actually, it's not the real reason. The real reason is so when we make the definition, maybe it's in the beginning of 19th century, and when we get the truth, it might be 19th century. It's 100 years between. So in between this 100 years, we have many researchers, many teachers, or students. We get many contributions based on this definition. And after 100 years, we find we make a mistake, but it is quite late to correct it. Because after that, every definition is based on wrong one, so we have to continue this mistake. That is the reason we didn't correct it. Okay, this one is the move of electrons. You can see it here on the left-hand side. This one is the focus force, right? And we know the current is moved from this side here, but the electrons inside is moved counterclockwise, right? Right, here we need to define the reference direction of current. You know, we have the real direction of current, but why we need to define a reference direction of current? Think about this. Think about this.
Why we have to find this?
From the view of mathematics, from the perspective of mathematics, and tell me why we need to define a reference direction of current.
Why you need to?
Why we need to define?
Who is that? This who is that? Can you please? Why you need to find?
Why we need to define a reference direction of current?
Reference direction.
Yes, because we already have a real direction. Why we still need to define a reference one? Why we need to define a reference one? Have you ever considered all this?
I did it, but I can do a little. Because also when this one time is moving one circuit, he made some plugs, and I have learned this that for this equation maybe you know this is the mathematical equation, right? Yes.
And we say no, not this one. Maybe we have x1 plus x2 equal to maybe 4, and we have 3x1 minus x2 equal to 8. So this one is the equation area, right? So for mathematics, we know how to solve it, right? And we will solve it with x1 and x2, right?
Yes.
And I told you before, in our circuit, we also have a similar equation like this. So our job for our circuit analysis is solve that equation. That equation is KCL equation, and some maybe constant, right? Maybe like Ohm's law, maybe like this, something like this. So in the form of this one and this one, we say all mathematical equations, and our job is to solve it, right? Okay, but we
x1 equals
x1 and x2, they doesn't have direction. But for this one,
have direction.
I,
Yes.
it has the value and it has direction as well. But do we care about the direction?
No, for this one we need to care about
How?
direction. But
How about
this
this
we
one?
have to care this direction.
Yes, but do we need to care about the real direction? The real direction? We don't need to care about the real direction, right? Think. If we calculate I equal to 2 minus and here, what does this mean?
This
It's opposite
opposite.
to the reference direction, right? So we
Yeah.
don't need to care about the real one because we can use the reference direction, and if the reference direction is the same as the real one, it's positive.
Yes.
If it's not the same one,
So
it's
negative.
negative. Okay, so from the mathematical perspective, we find we don't need to care about the real direction, right? So we just care about the reference direction. Okay, go back to our post. Here, in most of the cases, in some of the cases, we know the real direction, but in most of the cases, we don't know the direction of the current. So, in this situation, we need to assume a reference one. The reason is, in our mathematical equations, if we don't know the real direction, if we define the reference direction, we can see the real direction from our result. Okay, that is the reason we have the reference direction. Okay. For a simple case, maybe for a simple case, maybe we have a current source here.
Yes.
We have another resistor here. Do we know the direction of R? Of R. Do you know the direction of R?
Positive, negative.
It's
Positive.
not this direction, right?
Yes.
Since it's a single case, we know the current is start from the opposite side of the source. Okay. But look at this figure. We know here, okay, start from here, right? Go here, right? We know how to here. Here, it goes to one, go here, another go here. Go here, and go down here. But for this one, on 4, do you know the direction? The real direction of I on 4?
This is a parallel circuit,
So it might be this one, since it's go here and go here, right? It might be this one as well, since here it has another current go here and here. So we don't know the real direction of current inside R4.
For this, we have a current here. So this current can going to be 2 current.
Yeah?
If this I2, I5, we can do it.
The real direction is decided by the R of R2, R3, and R5 and R6. So it doesn't depend on itself.
Okay.
Okay. So because when you see here, can't go here, can't go through here, right? Can't go here and go through here as well.
Yes.
So here it might be this way and might be this way as well. So we cannot just to find out the direction from the figure. So we have to calculate and then find out the direction of it. So we need to, what we do we need to do now? We
Find
need
the
to
equivalent
find
value.
a reference one. Okay, so we don't need to care about the real one. So we just give it arrow. Okay, and one, this one or this one, but just one. So when the result is positive, so this one is direction.
Yes.
If the result is negative,
This
the
one.
real direction is this one. Okay. Okay, look at this figure. There are 2 selections of reference direction. And we just have before here, for A and B, this one is a conducting line. Okay, so we have a positive electrons move from the down to the up.
high potential to low, for plus to minus.
Yes, just look. The right direction is chosen as either. So the left one is up, for the right one is down. Okay, so let me see. The electron moves. So for the first one, it moves up, right? So the direction is the same as the arrow, right? That means it's positive. So from the second one, you can see the direction
Negative.
is different with the movement.
No, the same, but this direction
No.
is
The direction here, like this. Okay. So the real direction is this one, but our positive, our reference direction is this one. So the value should be minus one. You know?
Master, can I get explanation?
Okay. So it's like it's the same actually. Go back. So here, this one and this one, the figure is the same. We have the same figure, right? We have the same electron, right? So we have, when it moves, we have the same real current direction. Okay, but the arrow is the reference direction. So we say it's the current should be 5A, okay? The real current should be 5A. So when it moves from here to here, the direction, real direction is the same with that. So we have the value used to use 5 to stand for the value, and we use the sign to stand for the direction. If it is the same, we use positive. If it's not the same, we use negative. Understand? Okay. Okay, there are two types of current of our general cases, the DC and AC. What does that mean? We except those two cases, we have some other type of sources. We have it. Have you ever seen like maybe some wave like this? Have you ever seen some wave like this?
yes.
But it's not the common case we see in our life, right? The most common case in our circuit analysis or in our life is the DC and AC.
AC.
Okay. Here, the DC, the figure is like this. Here is the t, the time. Here is value of I. So the line should be a straight. A current remains constant with time. We say it is the direct current. In our life, the direct current item, you can see, or source is the battery, right?
Everywhere.
Here, I see DC here, and a current, okay, AC circuit, a current that varies with sinusoidal with time is called alternating current. Okay, it's like this. So where do we have an alternative current? We say in the plant.
This one.
Okay, in our building, we use electric current as well. But
AC current.
here, the main power produces it from the power station, right?
Yeah.
Okay, now we are going to see voltage. Voltage is another important variable of circuit analysis. Here we have A and B. There are the 2 points. And here we say point A has a potential 5 volts, and B we have potential 0 volts. And if we connect elements between points A and B, and we'll have a current. Because we have potential difference, right? If we have potential difference between 2 points, we must have a current between them.
Yeah.
And the direction of the current should point from the
High
high
potential
potential to the low potential. So, what is this? If you know the magnetic field and the electron field. So, the direction is the same as what? The direction of R is the same as what in the magnetic field, electromagnetic field. We have another thing, another concept in the magnetic and electric field. What is it? What is the direction? We say it's E. So the direction of E is also from the positive high potential to the
Negative.
potential. Okay. Right. So energy is also called potential difference. Okay. So it is the energy required to remove a unit charge. Remember, it's a unit charge, right? Through an element, and the unit is V. We said it's volt. And here is the equation or the definition of a V. Similarly, we didn't get the V directly from this equation. How do we get V? We say current I and voltage V. We all get it from the main equation with KVL and KVL. We didn't get it from this equation in most of the cases. Okay. So, but we should know. Okay. In some manipulation, we use this equation. We should know where it comes from, right? Okay, since it's a potential difference, here we have VAB. What does this mean? VAB means
The
VA
difference of-
minus VB. Okay,
The
so
difference of potential A to B.
yeah. So if we remove the position of P and A, we'll get to minus
Minus 5.
5B. Okay, everybody know this, right? This figure shows the positive charge moves from high to low potential, and it will yield energy. Otherwise, it repels energy. Here we have two electron field. Electric field. The E is electric field, right? And we know the direction of E. This one is from the high potential to the low potential. So in the left-hand side, it's pointed to the right. To the right, yes. Here, it's pointed to the left. And if we put a positive electron here, and move it from left to the right. So we say it's do positive work and yields energy. And here, on the right hand side,
It's
the
negative.
direction of electron field is changed. Okay. Similarly, we also put a positive electron here and move it from left to the right. And this one is
Negative.
external force. Okay. So it will do negative work and it requires energy. Okay. And we put a negative electron here and move it from left hand side to the right hand side. We know
This positive one. This one for
it's
negative.
the negative work
But
and
this one is positive.
repels energy. And if we put here,
Positive one.
do positive work and yields energy. And we will find these two cases is the same, right? And this case is the same. The same means do the same work and yields the same energy. Okay, so we just talked about the reference direction of a current. Now we're going to talk about the reference polarity of voltage. Here, this one is the example. VAB is 9V. If point A is positive and point B is negative, VAB is 9V. Here you can see if point A is minus, point B is positive, VAB
Minus
is
minus.
minus B. So what is VBA? Yes, good. So, the sign of voltage value is related to the reference polarity. That is mean if the same that if the real direction is the same as the reference one is positive, and if it's not the same, it's negative. What does that mean? It means the sign is stands for the direction. Okay. Okay, now we're going to see the 1.5, the power and energy. Power is the time rate of expending or absorbing energy, and we use W to measure it. This one is the equation to describe the mathematical equation between Q and W. Okay, so we can have a short derivation from here. This one is the most basic one, right? And here we put the dq in the denominator and dq in the denominator as well. And we get this equation. The left side, dw over dt. From the definition of u, we know it's right. And for the second one, dq over dt, we know I. So we get p into vi. That is where this equation comes from. So we say this one is from definition, and after derivation we find the p. We cannot use this one to measure it. We use p into vi. That is mean when we get the v and when we get the I, and we get the p. So this equation is for the instantaneous power p. P equal to vi, and in some books we use p into ui. Okay. Now, we need to consider if the power has a direction.
Power direction.
Does power have direction?
No.
No. Power has direction?
No.
No. No, power doesn't have direction. Okay. Does power have signs?
Yes. When we observe and supply, we have
Yes. You say power is a scalar with no direction, but signs. We use signs to describe its use or absorbing energy.
If you observe this plus, it will suffer.
Not in most of the cases. You know, we have positive sign convention and we also have negative sign convention. The P is different in those two cases. You know, so, but for our students, it is better to maybe to just use one. You use positive sign convention or use negative sign convention, and you just remember one case and forget others. That is the most good case. Okay, let us see an example here. This one is resistor. Never mind. Just treat it as electric elements. Here we put the 4V here, and the reference direction is selected as this one. This one is positive line, and the current go inside from the positive side. Okay, so this case, our P equal to UI. Our U is 4, right? Our I is 3. So it's now 3. This case of selection of reference direction. See here, for voltage we select here the positive right. For current we select the arrow as reference direction. This kind of selection is called positive sign, is called passive sign convention. The currents go inside from the positive sign. This one is called passive sign convention. Passive sign convention is generally for the passive elements. Do you know the definition of passive elements? Do you know passive elements?
Active elements. This is
Yes. We have active elements as well. We also have passive elements. So what type of passive elements do we know?
resistor capacitor indices.
Yes. Good. So what type of active
Current
elements?
voltage, transistors.
Okay, so source is the general from the second figure. So in this case, the reference direction is selected the same as previous one, but now we change the reference direction of current in this case.
Yes. So this
Okay,
is
so
supply.
now we can see the current is flowing side from the negative
Negative
side,
to
okay,
positive.
to the positive side. Right. So now we know for this case, the sign, the I should be
Negative.
-3. Okay, so be -3, and the the voltage is still 4. So the P is -12 volts. Okay, but it's not the same, right?
These are the same because this is supply. and
This
this-
one is
Absorb
absorbing energy. This one is
This is supply.
supplying energy.
That means I have this one. I give him this one. That means I minus this supply. So this one is minus.
Okay, now we're going to see the passive and active sign convention. I just talked a little bit before, okay? The definition of passive sign convention is satisfied when the current enters through the positive terminal, okay? So, and the P equal to VI. The active sign convention is satisfied if the current enters through the negative terminal. So our P equal to -VI. What does that mean? So when we get a circuit, generally when we get a circuit, the direction is not given, right? The
But
real
given-
direction is not given, and the reference direction is not given as well.
So given the source and this
We
current
give
direction.
the direction by ourselves in most of the cases. Okay, in our book, in the beginning, maybe in some practice, they give you the direction. That is because they want you to practice how to use or calculate the I. Okay, but in most cases, we just have the circuit figure.
Like chapter 4 and one
Yeah.
part of chapter 3.
Yeah, they doesn't give us any direction. Okay, sometimes they give direction of the source.
Yeah,
Okay.
like this.
We know the direction of the current source or the voltage source, but we don't know any other direction.
Of element.
Maybe inductor, capacitor, we don't know the direction of it. So in that case, we need to assume the reference direction by ourselves, right? Okay, that is why we need to learn the passive or active sign convention. What does that mean? For passive elements, we use passive sign convention. That means this one is resistor, right? We give the direction of the U and the I to this one. First, we give the direction of V, and next we give direction I. We say this one is the passive element. For passive element, we use passive sign convention. Understand?
Yes.
So, the passive sign convention, the currents go inside from the positive side. Okay? So, we know the passive elements. Without this one, we also have inductance, right?
Mhm.
So for inductance, the reference direction of current or voltage is still like this. And we also select the reference direction of the inductor like this, going inside from the positive one to the negative. And we also have capacitance.
Mhm.
Okay, so we also assume a direction like this, positive, negative, and the reference direction of current is go from the positive side. Okay.
Negative.
How about the active sign convention? What is the active element?
Active element stands for voltage source.
Yeah. This one is the current source.
Yeah.
Okay, we already know the direction of the source.
This
Like
one.
this.
Yeah.
So, this one is the reference direction of current source that we choose. So, the reference direction of U should be like this, because this one is the active element. So, the reference direction is active side convention. The columns go inside from the negative side.
Negative sign is okay.
Another type of element is voltage source. This one is also an active element.
Yes.
Yes. So for active elements, we already know the real direction of the voltage, right? The positive sign is here. So now we can assume the reference direction of current.
Current.
It should go inside from the
Positive.
negative side. So it's like this.
Yes.
So it is the same, like the same we started in the previous flow, right? Just different understanding. Okay, so we define the passive elements, and we use passive sign convention for the passive elements, and we also define the active elements, and we use the active sign convention for the active elements. So I think it is easy to understand the concept. Okay. So here, one more question. We know resistance or resistor is a passive element, but inductor and capacitor, they can store energy and they can release energy as well.
Yes.
But why is still a passive sign? Why is it still a passive element? Because we can see for active element, we know it can release energy, right? But for inductor and capacitor, it can store energy and it can release energy as well. So why it is not an active element?
Because we are using this capacitor and inductor like this inside it. So sometimes this
I
is both.
I know,
Resistance is there.
but in our book, it has definition of active element. Active element means it always releases energy,
Yes.
but for passive elements,
Yes.
it can release energy and it can
Everyone.
store energy, but the energy released must smaller than energy stored. So that's the definition.
Mhm.
Okay.
That's why we use capacitor from this high voltage.
Yeah. So that is maybe easy. That is an easy way to understand the passive sign element, the passive sign convention, because we use this convention in most of our cases. Okay. And in these cases we have here. Here is another question. The equation will be 0, 2. Here we have P equal VI, but in another convention we have P equal C.
Here.
Is it good? It's not good, right? We don't want to remember two equations. We just want to remember one equation.
Just remember this direction of current.
Yes, so in most of cases, we just remember this one. Okay.
This equation is only depend on current direction. If I just know this V equals VI, VI,
But actually, I just remember this one, and if the value is positive,
this is positive.
yeah.
If this I value is positive, this is positive. If I value is negative, this is negative.
Okay, here I see a V here. For this case, when P is greater than 0, it absorbs energy. Okay, for this case, when P minus 0, it supplies energy. We find it's not related to the sign convention. Okay, what is the sign of inductor or capacitor's power onto the passive sign convention? Does it absorb or supply energy? say inductor is the passive element. So generally we use this one, okay? So in this one we use PPVI. So because in our course we don't have too much circuit elements. We just have resistor, capacitor, inductor, right? So we just remember for those three we use this one, okay? And for the source, do we use this one? You use both two, but for me I just use this one.
I just remember this current direction. This okay for me.
Okay. Oh, and never mind. If it is easy for you guys, you can continue. But for me, I just tell you my method. My method. For me, it is better to just remember this one.
This one.
Yes, because this one is for the inductor, for the passive elements. For the active elements, I just remember if it is
Negative.
positive. P equal to VR.
Here, for active element is negative. P equal minus V.
Release energy. I
Yes.
just remember it always release energy. Okay, so I don't need to care about the equation. I just remember it in my heart. The energy always release energy. Okay, so that is why I just use P to VI. So just change. Just remember it's release or stored energy. And just use this equation. So here is another question. Generally, for passive elements, non-associated reference is in prior. Why? Nothing here. Convention of active to passive. Here is, from this page, I explain why we use P equal to VI. Here, we see the expression of power P has two forms, P equal to minus VI and P equal to VI. And then here, we just use P equal to VI for calculation in limits. Okay, for energy. Energy is the capacity to do work, and we use joule to measure. There are one important law. It is called the law of conservation of energy. Okay, this word is wrong. Okay. In a circuit, energy cannot be created or destroyed. The sum of all power supplied must be absorbed by another element. The sum of all power at any time instance must be zero. The sum P equal to zero. So this equation is the mathematical equation of this law. Here is the P equation. And if we integrate this equation, we get the energy equation. Our energy W is equal to P dt, integrated from T0 to T. And we already know that P is equal to VI, so we also can use this equation to calculate our W. So, in our homework, generally we use this one.
Yes.
Or this one as well.
This one is same. The P equal V
Yes.
is the equation. And look, for this summation of P, epsilon energy plus of energy equals 0.
Yeah. Yeah.
Because how much is it?
Because the energy cannot be created or destroyed.
Yes.
It just can be transferred. So here is the state grid. You know, in England we have national grid, and in China we have state grid. It's a big electric company, right? This state grid use watts per hour to measure energy. We didn't use joule to measure energy, right? 1 kilo watt hour.
1 kW.
is 1 degree.
1 unit.
Okay, now we're going to the circuit elements. A block box like this is used for circuit elements. In our Chinese book, we use this one for resistor. In Chinese book, we use this one for resistor. Do you know? You know? That means that in Chinese book, it is not the same as international
Some of
standard.
book, that's also the some of example, this is very good.
You can see from here, we use the block box for resistor. So when you see some cases in Chinese book, the block box stands for the resistor. But in other books for other countries,
Like this.
it's like this. Okay, like point. Okay.
But the simulation of circuit, when you like make a simulation of computer, this resistor is like this box, like this. When you use
Yes, but-
MATLAB or some
Yes.
simulation application for solving circuit, and this resistor is
Different countries use different standards.
yeah.
Okay. Anyway, I just want you guys know what it mean. Okay. So I think it's already 9 points. Okay, we already ran 1 hour, so it is better to